So we're just going to talk for a moment about peer-to-peer architectures and how they're different and some advantages that they have. One of the main differences in a peer-to-peer architecture is that there's no always-on, uber-fast, uber high storage server. It's kind of like everybody's a server. And so everybody's a server and everybody's a client. Any end system can communicate with any other end system. So arbitrarily, they can connect. Remember, in a client-server scenario, the end systems only connect to a server, which is usually just in one spot. It has a lot greater resources in terms of speed and capacity. One of the challenges and properties of this P2P architecture is that there may be changes in the connectivity of the devices, right? Where if you might move your computer from one place to another place and get a different IP address when you go to a different network. That doesn't happen to a server because the server always stays there. One file that we're going to consider, did I say file? One problem that we're going to consider is file distribution. And that means, how do we get this file from this computer to all the other computers? So how do we download a file and get it one copy on one computer to all the computers in the system? So what we're going to do is we're going to mathematically model that in a client-server scenario and in a peer-to-peer scenario and see how they compare based on some different factors. So we're going to call U sub S the server upload speed. We're going to call U sub I the upload bandwidth of each of the peers, that's each of the hosts, those regular computers, and we're going to call D sub I the download speed for each of the computers. Do these make sense? We're going to say we have big N total clients in the system. Okay. So given this setup, what are the limiting factors? So depending on what these values are, we're going to have different things that could occur. One situation is that kind of the bottleneck, or what could be the bottlenecks in this situation? Can you think about it like that? Well, actually, we're just talking about client server. Did I say that? Sorry. Okay, so that was a great response because I didn't clear. So let's just consider client server first. All right, client server should be the simple scenario. There's clients and servers. So what factors would, in a client server setup, cause the system to be bottlenecked? Well, we're only sending the file from the server to all the clients. Okay, so the client download speeds may be a factor. So what's that? And how fast the server. So if we had really fast clients, but the server has a slow upload speed, then the server just can't get it out to everybody. So we kind of have two different scenarios, and that's what this equation represents. So the distribution time in a client-server scenario is whichever one of these is bigger. We've got these two quantities, okay? The first quantity, these are easy to understand. The first quantity is related to the server. How many bits does the server have to put out there? Well, it has to put out the whole file, that's F, n times, because it's got to send a complete copy of the file to every single client. Right? The server has to send the whole file, n times. So this is how many bits it has to send, nf. And how fast does it send? It sends at a speed, it uploads at a speed of us. So nf over us is the speed that the time that it's going to take the server to send that file out that many times. Does that make sense? So if the server is the slow part, then this is going to be the bigger time, and that's going to determine how much time it takes to get the file distributed. On the other hand, it might be that we just have a super slow client and he's holding everybody back. That makes sense. If you've got one guy down here that can only download it, a 56K modem, then the server can send it out to everybody, but he's just still waiting on this guy to finish. That makes sense? So we found the minimum DI, that's the minimum download speed of all of the clients, and we take the file size divided by that speed. So this is the time that it takes the slowest client to download the file once. So those are our two potential bottlenecks. Whichever one of those is bigger is what the time to distribute the file is in a client-server scenario. Does that math make sense? It's pretty straightforward. So depending on what these values are, it could look very different. But this is a scenario that models it. So now we're going to do the same thing in client in peer-to-peer. So we're going to have these two constraints in peer-to-peer, which is how long does it take to upload the file to everybody, and how long does it take the slowest guy to download it. But we have one more scenario, right? Because in peer-to-peer, everybody's a server. Is it clear what that is? No? Let's look at it like this. So if everybody can be a client and a server, then the server just has to upload it once so that somebody else gets a copy of it, and then that guy can upload it to somebody else. Does that make sense? This whole setup does assume that all the computers just magically know who to connect to. And in actuality, that couldn't happen, right? They'd have to know, I need to talk to this guy to get this part of the file. But we're going to kind of assume it in an ideal case. So now we have three quantities. The first quantity is, this is how long it takes the server to upload the file once. So that's the full file, F bits, divided by the server's upload speed. So this is an improvement from before because the server doesn't have to upload it n times. It just has to do it once. And then it's sharing the load of the additional distributions to other clients. We've got the same one, which is whoever the slowest client is, has to download the file once, so that's F divided by the minimum DI. And the new one that's interesting to us is we know that the file has to be distributed from every person to, all the bits have to be distributed to everyone. So the total number of bits is NF, but we get to share the upload capacity of the whole network. And the upload capacity of the network is the server's upload speed plus a sum of all the upload speeds of all the clients. So this is what makes it peer-to-peer, is that we don't just have to upload it from the server, and that's the only choice, but everybody can upload. And that means other people could download from that other server, other people could download from that other client's upload. And in that case, that client is acting like a server. That's peer-to-peer. So this is the interesting part, is that as we add more computers to the network, right, in the client-server scenario, that just gets worse, right? Because the more you have, the more times you have to distribute, that's more load on the server. Whereas in a P2P scenario, the more clients that you add, yeah, you have to distribute it more, but you get their capacity also added in, their upload capacity. Does that make sense? So you get this trade-off effect. So now I'm going to show you this graph, which the authors chose some reasonable amounts for F divided by U. So that's the time that takes the download time for a client. They're going to assume for this that all clients have the same download speed. So all the DIs and all the UIs are the same. So it takes, if F divided by U is 1 hour and US is 10 U's, so the server has 10 times the upload speed of the clients, and we're assuming that the minimum download speed is greater than the upload speed of the server, which that's probably reasonable too. Then this is the graph that we get, which should make sense, that as we add more and more devices to the system, right, the client server continues up linearly. All right, let's go back and look at that equation to make sense of that. Right, as we add more and more clients, which one of these terms dominates? NF, right? There's no N in this, so it's going to be kind of fixed with respect to N. So as we add more and more clients, this thing just blows up, right? It just increases linearly because there's an N there. What do we see here? Linear increase. Makes sense, right? So in a client server scenario, the time to distribute this file, that's the minimum distribution time, increases linearly in the number of computers in the network. However, we get this nice looking chart here for peer-to-peer, where as we add more systems to the network, the minimum distribution time doesn't go up linearly. And why does it not go up linearly? Can you kind of sum up what we said? All right, because they're sharing the bandwidth. They're sharing that upload responsibility. So that's peer-to-peer, and you see how with a large number of N, we get a nice payoff, and with these particular values set. Does that make sense? So this kind of shared responsibility and sharing the bandwidth and often saving time, right, making it more efficient to distribute this file is why P2P has been popular.